What if I could start with nothing more than a login form, identify the database behind it, find its tables, see the columns inside them, and finally recover the data stored there? That's exactly what we're going to do today, inside my own Windows Lab. And I'll explain every SQLMap option along the way, so you understand not just what the command does, but why we're adding each part. Before we start, this is a deliberately vulnerable machine on my private lab network. The target is 192.168.56.105, and I have permission to test it. The goal here isn't to attack random websites. It's to understand how SQL injection testing works, and more importantly, how defenders can find and fix it. First, I want to know exactly which SQLMap version I'm working with. The command is simple: SQLMap followed by --version. The -- tells SQLMap that we're using an option rather than giving it a target. Here we can see I'm running SQLMap 1.10.6. Before giving SQLMap anything to test, let's first look at the web server ourselves. I'm using curl here. The -I option asks the server for the HTTP headers without downloading the full page. And look at what we've already learned. The server is Apache 2.4.58. It's running on Windows, and the application is using PHP 8.2.12. The response code is 200, which tells us the login page is reachable. Now I want to inspect the actual HTML and look for form input fields. I'm piping the output into grep and using -I, which makes the search case insensitive. I'm specifically looking for the word input because that's where HTML forms usually define fields such as username and password. In this case, the important point is that we're moving from server-level information to the actual parameters the application accepts. Now we finally bring in SQLMap. This command looks much longer, but every part has a specific job. First, -U tells SQLMap which URL we're testing. Next comes --data. This is important because the login form sends its values using a POST request, so we're giving SQLMap the same data the browser would send. Then we have -p username. This tells SQLMap to focus specifically on the username parameter. Instead of testing every possible input, we're telling it exactly which parameter we're investigating. And finally, --batch tells SQLMap to automatically choose the default answers to its interactive questions. That makes the demonstration repeatable instead of stopping for input every few seconds. And this is the important moment. SQLMap confirms that the username parameter is injectable in this lab. It identifies several SQL injection techniques, including Boolean-based, error-based, and time-based blind injection. Notice that we're not guessing blindly anymore. SQLMap has tested how the application responds to different database conditions and identified behavior consistent with SQL injection. It also identifies the backend as MySQL, while the web stack is Windows, Apache, and PHP. Now that we've confirmed the injection point, the next question is simple. What databases are behind this application? That's why I'm adding --dbs. Notice something important. I didn't replace the previous command. I kept the URL, the post data, and the vulnerable parameter exactly the same. I'm only adding one new option. We're moving one step deeper in the same investigation. --dbs tells SQLMap to enumerate the available database names. SQLMap finds 6 databases. But the one that immediately interests us is lab_db, the application database created for this lab. Knowing the database name still doesn't tell us what's inside it. So now we add two things. -dlab_db tells SQLMap which database we want to investigate, and --tables asks SQLMap to enumerate the tables inside that database. And we get one table, users. Now we know where the application's user records are stored. But a table name alone isn't enough. We need to know what fields the table contains. That's where -T users comes in. The -T selects the table, and --columns asks SQLMap to show the columns inside that table. Now we have the structure. There is an ID, a username, and a password field. At this point, we know the database, the table, and the structure of the data. Now comes the step that ties the entire chain together. We've already identified the injection point. We know the database. We know the table. We know the columns. So now I'm adding --dump. This tells SQLMap to retrieve the records from the selected table. And there it is. 2 test records from our lab database. SQLMap also saves the dumped table as a CSV file, which is useful for documentation and further analysis. And this is the part I want you to remember. SQLMap didn't magically jump straight to the database. We followed a chain. First, we identified the web application, then the input parameter, then the injection point, then the database, then the table, then the columns. And finally, the records. That's the real workflow behind automated SQL injection testing. Now let's flip the perspective. If SQLMap can reach this far, the application has a serious problem. The first fix is to use parameterized queries or prepared statements instead of building SQL queries directly from user input. Input validation helps too, but it should not be your only defense. And database accounts should have only the permissions the application actually needs. A login form should never become a path to an entire database.